Hi and welcome to maths class. Today we're looking at composite and inverse functions. So what we're going to do is a little bit of revision, revise what we already know about composite and inverse functions, and try to bring a few of those things together, as well as what we know about increasing and decreasing functions. So it's a bit of revision and it's a bit of tying everything together. So composite functions, let's remember what that means. If I've got a function y, which is g of f of x, then f of x is my inside function and g of x is my outside function. And I call that g(of) of x. So I start with my value for x and I put it into f, and then whatever value comes out, I put that into g, and then whatever value comes out, that's y. So all the values that can go into f of x, that they make up the domain of f, and what comes out of f makes up the range of f. Now the range of f has to fit into the domain of g, so it must be a subset or an equal set to the domain of g in order for this function to be defined. Then the domain of g, which is the values that come out of f of x, go into g of x, and what comes out is the range of the whole function g(of) of x. So let's remember that g(of) is defined only if the range of f is a subset or equal to the domain of g. And the domain of the whole thing is equal to the domain of f, the inside function. All right, let's revise inverse functions. Inverse functions are undoing functions. So if I have some function f of x such that I take my values for x, I put them into f and I get y, the inverse is the function such that if I take those y values and put them into the inverse function, then I get back to x. So some simple examples that we know are, let's say if f of x is squaring, then f neg 1 will be square rooting, of course with some other restrictions. We learned about inverse operations a long time ago. If I'm going to add here, then I'm going to subtract here to get back to where I started. All right. And the way we find the inverse function is we swap x and y. So y is equal to f neg 1 of x, and the domain of the inverse is equal to the range of f, and the range of the inverse is equal to the domain of f. That's just a quick bit of revision. So here are some of the key skills that we're going to look at. We need to make sure we know how to express a function as a composition of two functions. This is also important when we do differentiation and we use the chain rule. One of the main places that people go wrong when using the chain rule is they actually can't do this step. So we're going to practice that. We need to make sure we can find the composite of two functions. So if given f of x and given g of x, can I make g of f of x? And we need to make sure we know how to find the inverse, including and importantly showing all appropriate working. So now I'm going to look at each of those key skills with some examples. So my first key skill is expressing a function as a composition of two functions. So I've got this function here, h of x equals cos of x squared plus 3. So hopefully you can see that I've got an inside function there, which is x squared plus 3, and an outside function, which is cos x. So I'm going to define two new functions. I'll use f of x as my inside function. So let f of x equal x squared plus 3. And let g of x, that's going to be my outside function. G of x is cos x. Then h of x is going to be g of f of x, or g o f of x. Either of those two. These are equivalent statements. They're the same. Okay, so the important thing is that I have separately defined the inside function, x squared plus 3, and the outside function. Okay. My next skill is kind of related to that. It's the same thing in reverse, finding the composite of two functions. So this time I'm given f of x and I'm given g of x, and I'm asked to find f of g and g of f. So f of x is x cubed, g of x is e to the power of x. So what I'm going to start with is fog of x. So I'm going to rewrite fog of x as f of g of x, and then inside that bracket, I'm going to put g of x. So instead of writing g of x this time, I write e to the power of x. And now what I do is I'm looking at f of e of x, which means I have to take f of x, but I replace my x with e to the power of x. So this is going to be f of x is x cubed, but instead of x cubed, it's going to be e to the power of x cubed. But I can't leave it like that because that can be simplified. I've got e raised to a power inside a bracket and then raised to another power. So I multiply those powers together, which gives me e to the power of 3x. All right, now let's look at g of f. I'm going to do the same thing. I'm going to rewrite that as g of f of x and then replace the f of x with x cubed. And now g is e to the power of x, so I'm going to have e to the power of, but not x, it's going to be this function x cubed. So this is e to the power of x cubed. That cannot be simplified any further, so I'll leave it like that. But I'll take a moment at this point just to remember, we've done this before, but just to remember that f of g is not going to give me the same function as g of x. These are quite different functions and they will look quite different. So now I'm going to find an inverse of the two functions, of these two functions that I'm asked for. That's my third key skill, finding an inverse, and I need to make sure I show all the working that needs to be shown. So first I'm finding the inverse of f of x. That's a nice easy one. F of x is x cubed. So f of x is x cubed. I'm going to define let y equal f of x. And the reason I do that is so I can write y equal x cubed. And now I can write swap x and y. Remember this? Swap x and y for the inverse to find the inverse. And I'm left with x equals y cubed. Okay, so once I've swapped x and y, I need to rearrange this equation in order to make y the subject. And in this case, it's a simple case of raising both sides of my equation to the power of 1/3. X to the power of 1/3 is going to equal y cubed to the power of 1/3 is going to be y to the power of 1. So I've done it. I've found y equals x to the power of 1/3. I'm not quite done. I wasn't asked to find y. I was asked to find f neg 1. So I will write f neg 1 of x equals x to the power of 1/3. You could write that as the cube root of x. It's the same. All right, my second task is a little more challenging. G of f. I need to find the inverse of g of f. And here's g of f up here. I've already done it. E to the power of x cubed. So I start by writing let y equal g o f of x. So now y equals e to the power of x cubed. And now I swap x and y for the inverse. Swap x and y for inverse. And that gives me x equals e to the power of y cubed. So I need to rearrange this equation to make y the subject. The first thing I want to do, at the moment y is a power, so I'm going to take the natural logarithm of both sides of this equation so that I'll have just y cubed on the right hand side. So I've got log base e of x equals y cubed. I don't need to write equals log base e of e to the power of y cubed because I know that's going to simplify. That's the reason I've chosen to do log base e of both sides. Okay, so log base e of x equals y cubed. I now do the same thing as I did before. I raise both sides to the power of 1/3. So I've got log base e of x to the power of 1/3 equals y, which means that g o f neg 1 of x equals log base e of x to the power of 1/3. And I'm done. Okay. So that's the worked examples I'm going to look at. There's a little bit more theory that we need to discuss though before we go away. How are we doing for time? 15 minutes? Yeah, let's finish. I won't start a new one. I'm going to talk a little bit about strictly increasing and decreasing functions, and I really need to talk about these in the context of inverse functions. So first of all, let's remember what it means. A function f is strictly increasing if a and b, which by the way are elements of the domain of f, if a greater than b implies f of a is greater than f of b. And I find it much easier to think about if I increase x a little bit, then that is also going to increase f of x, okay? But I need to have two numbers here, a and b, defined because I've got my starting point x, and then just slightly greater than that is a second value for x. So the first one is b and the second one is a. The bigger one is a. Now, a function f is strictly decreasing if the opposite is true. A is still bigger than b. Now f of a is smaller than f of b. So you can see this clearly on a graph. A strictly increasing function has a positive gradient. A strictly decreasing function has a negative gradient. But remember that horizontal points of inflection are included in that. If I think of a strictly increasing function, at the horizontal point of inflection, if I go slightly to the left, I'm going slightly down, and if I go slightly to the right, I'm going slightly up. So my horizontal points of inflection are included. But it looks like a positive or zero gradient all the time for increasing and a negative or zero gradient all the time for decreasing. Now that means that these functions are going to be one-to-one functions. And if you remember what that means, it basically means it passes the vertical and horizontal line test. If I put a vertical line through my function, I'll only ever meet it once. And if I put a horizontal line through my function, I'll only ever meet it once. And that is what makes it so important for the fact that my inverse function is defined. All right, now, first of all, let's go to this actually. What I've got there in the smooth curve is y equals f of x. I don't know what function that is, I just made it up. And then in the dotted line, that's the inverse function. So let's just look at f of x first of all. If I take my ruler and I pass it anywhere through that function, I only ever meet it once. Vertically, horizontally, same deal. I only ever meet it once. Now have a look at what happens with my inverse function. Same deal, right? Same deal. Okay, so they're both one-to-one functions. They're also both strictly increasing. This has got a positive gradient all the time. This has got a positive gradient all the time. Although it looks like maybe that's horizontal and maybe that's vertical, but I don't think so. I think that they are positive gradients the whole time. So if f is strictly increasing, then its inverse is also strictly increasing. And the opposite is true. If f is strictly decreasing, then its inverse is also strictly decreasing. And we can see that here. Here's another sample function. It's reflected across the line y equals x. Here's my original y equals f of x. Here's its inverse y equals f neg 1 of x. They're both one-to-one functions. They pass the vertical and horizontal line tests. And they're both strictly decreasing. The function has a negative or zero gradient throughout. Okay, so that's another key point that we need to remember. I don't have any examples with relation to that. However, if I look at the examples that I just did, no, that's the wrong page. Where'd I put them? Over here. Yes, that's the one. I started with y equals x cubed. That's a strictly increasing function. And y equals x to the power of 1/3 is also strictly increasing. The fact that it's one-on-one makes it possible for me to find the inverse. And in fact, this is also a strictly increasing function, and so is its inverse as well. All right, the domains of these two functions are different, but they are both strictly increasing. Okay, that's the end of our video on composites and inverses.